This is AQA, A-Level Physics 2021, Paper 1, Year 1 content. As per usual, can't show the paper on the screen unfortunately, otherwise AQA will get the whole channel deleted, like they almost did in the past, but links to paper and mark scheme are in the description. If you find this helpful, please leave a like and consider putting a tip in the tip jar by clicking the super thanks button. It really goes a long way to helping me make these past paper videos. Question 1, we have some information about nucleus X. We're being asked to find the number of neutrons. So let's just find out what we have here. Now, specific charge, now I always like to write it as charge divided by mass because it is a charge to mass ratio. There really isn't another symbol for it, and even if there was a symbol for it, it's a good idea to just write it down as Q over M. It's charge to mass ratio. And of course we know that just looking at the unit, coulombs per kilogram. And we have the kinetic energy, KE, EK, doesn't matter, 215 mega electron volts guaranteed. We're going to have to turn that into joules at some point. So find the number of neutrons. 3 marks, not a super easy one to start off with, but we can of course find out the charge, can't we? Because we have mass and we have charge to mass ratio. So therefore we can do charge divided by mass times mass should leave us with the charge. Okay, so charge is going to be equal to that 8.02 times 10 to the minus 26 times 4.39 times 10 to the 7, and that gives us 236 figs, might as well for the time being, 3.52 times 10 to the minus 18 coulombs. So we know that a nucleus is made up of protons and neutrons, and so, well, it's only protons that have the charge, so what we can do is find out the number of protons. If we divide by the charge of a proton, 1.6 times 10 to the minus 19, and of course the unit of this we could say is coulombs per proton, then the coulombs will cancel, we end up with protons on top, so that makes sense. If I'm sorting out powers of 10 plus 19 on top, so this ends up just being times 10 to the 1, so therefore that's the same as 35.2 divided by 1.6, and that gives us bang on 22 protons. Okay, so we have the number of protons, but now we have to go back to our mass. We can say that the number of nucleons, that is protons and neutrons, similarly with the whole charge thing, but we're going to do mass this time, is going to be the total mass divided by the mass of a single nucleon. Now yes, they are slightly different when you get to nuclear in year 13, but when it comes to just these kind of calculations, we don't care. So just like last time, these kilograms cancel, we just end up with nucleons on top. So again, this just ends up being plus 1 on top, so that's the same thing as 80.2 divided by 1.67, and that gives us 48. So we have 48 nucleons, so therefore 48 take away the 22 of those that are neutrons, and that leaves us with 26 neutrons. Lots of steps there, not the easiest question to start off with for this paper. 1.2, calculate the speed of X. So we had here kinetic energy being 215 mega electron volts. Let's turn that into joules, shall we? So of course each mega electron volt is 1.6 times 10 to the minus 13 joules if it's mega electron volts, and it gives us 3.44 times 10 to the minus 11 joules. Okay, we know kinetic energy is equal to half mv squared. We're looking for V, so therefore rearranging this, V is equal to the square root of 2 lots of the energy. I've just dropped the K, doesn't matter, divided by mass, so that is the square root of 2 times our 3.44 times 10 to the minus 11 divided by the mass, which was from earlier 8.02 times 10 to the minus 26, and that gives us 2.9. No, I guess we should go to 3 sig figs, shouldn't we? Because all our data is times 10 to the 7 meters per second, so roughly a tenth of the speed of light. Question says ignore relativistic effects. That's just something that's in there for all those people who were doing turning points, because when it comes to turning points optional module, you do have to take into account relativistic effects. That is weird stuff happening when you approach the speed of light. But of course that only applies in paper 3 part B for those doing that module. 1.3, pi plus meson decays to produce a positron. Let's write this out, shall we? Positron, it's an anti-electron, and an electron neutrino. Show how the conservation laws apply to this decay. Nice and easy. All we have to do, we can literally just write down this. We don't need to write a sonnet. We just say charge goes from +1 to +1 + 0. Lepton number, baryon, so therefore not true. The electron is the original lepton, so therefore it's 1 + 1, that is. Positron is an anti-electron, so therefore it's -1. And then it's just a bog standard electron neutrino, so therefore that has a lepton number of +1. Finally, baryon number, well, there's no baryons involved at all, so they're all 0. We don't really need to go into strangeness, I don't think. Oh no, that's for the next question. Okay, here we go. Because a pion does not have strangeness, it doesn't have a strange quark, but a kaon does. So that decays into an anti-muon, so again that's the positive muon, plus a muon neutrino. Explain how strangeness applies in this decay. Well, strangeness, let's have a think about this. K plus meson, that's going to be up anti-strange. It has to be up to begin with, we know, because we need to get a charge of +1. So up quark has a charge of +2/3, so then we need to add on a -3rd from the anti-strange quark there. Okay, so strangeness is strange. Its strangeness of an anti-strange quark is +1, but then these leptons by definition cannot have strangeness because they don't have any strange quarks, because they're not even hadrons. But it's okay, allowed, as this is weak interaction. How do we know it's a weak interaction? Well, it's because there are leptons involved. Therefore, strangeness is not conserved. We could add the extra thing in there, something that I always forget. Strangeness can change by 1. And it is. It's going from +1 to 0. Write down an equation for K plus that involves any hadrons. Generally, they decay into pions, so we know that we'll probably have a pi plus. But generally, you don't have just one particle decaying into one other particle. It has to be 2 particles. So we're then going to say a pi 0 as well. Charge is conserved, lepton number, of course, and baryon number. No baryons, no leptons, just mesons. So yeah, because strangeness isn't conserved, it would have to be a weak interaction, this, but that's okay, I guess. Oh, I hate it. Question 2, we have microwave transmitter and receiver. We've been asked how the apparatus can be used to demonstrate that the waves from T are vertically polarized. So we can rotate aerial such that T and R are parallel, then perpendicular to each other. Is that redundant? Probably could be. So parallel and perpendicular. If signal received decreases to a minimum when perpendicular, this shows waves are polarized. There we go. Question 2.2, we have the transmitter and it's sending signals straight to the receiver and then off a reflector as well. So what are we being asked? Explain what happens as M, the mirror, is moved further away. When my lot did this question, they saw it and thought it was to do with like Young's double slit and that kind of thing. But no, we just have 2 different routes. So we do have a path difference. So we can say waves take, or rays, whatever, take 2 different paths. When path difference is equal to multiple of wavelength, so we can say just n lambda, constructive interference occurs, at r that is, maximum is detected. When path difference is equal to n plus a half lambda, destructive interference occurs, therefore minimum is detected instead. Let's just finish the question off. So we've been asked what happens to the signal, so therefore as M moves away, signal will increase and decrease repeatedly. Is it actually going to reach 0? Not quite, and maybe it's worth us writing this. Will not be 0 because intensity of waves will be different. So therefore they won't cancel each other out perfectly. Suggest why Young's double slit equation should not be used in this setup where we have a loudspeaker. Interesting question. Now, a lot of mine, when they did this, they got the right idea because I drilled it into them that when it comes to Young's double slit equation, it is an approximation, and it assumes that we have a circular screen or a curved screen where all the distances are the same. Well, the distance is constant from the slits to the screen. However, here, look at the slit screen distance and look at the slit separation. They're very similar. And so what we can say is that the equation W equals lambda D over S is an approximation. We're going to say only valid if the slit screen distance is much, much bigger than slit separation. And that's it. It's only 1 mark. Wavelength is known to be about 3 centimeters. Deduce whether this arrangement is suitable for determination of value of the wavelength. So we can't use the equation. So if we can't use the equation, we're just going to have to use trig. Yes, we could use d sine theta equals n lambda, but we'd end up just having to do trig to get theta anyway, so we're not going to bother. We're going to go with path difference. So we want to know, what's the path difference going to be right at the edge of the screen here? So what we can do then is draw 2 triangles. So we have one ray that's going from this slit up to A. So we have a right angle triangle there. And then we have the other one going from the bottom slit. They're not going from the middle, of course. We know the bottom distances for each of those. That's fine. Let's go with the top one first. That's 0.45. Let's draw the other one while we're at it. So we said that this was 25 centimeters from the middle to the top there. So therefore, this is going to be 0.06 meters from the middle to the top slit, and then the same for the bottom slit as well. So this on the side is going to be 25, but take away, well, 6 centimeters. So therefore there's going to be 19 centimeters or 0. Do you know what? I'm just going to leave it as centimeters. That's fine. I'm going to change this into centimeters as well. This here is going to be 25 centimeters plus another 6, so that gives us 31 centimeters there. Okay, so let's use Pythagoras to find out. Let's just call this, oh, I don't know. Let's call them D1 and D2. Why not? So D1 is going to be equal to the square root of 45 squared plus 19 squared. D2 here is going to be equal to square root of 45 squared again, but now plus 31 squared. So this gives us 48.8 centimeters, and this gives us 54.6 centimeters. So the path difference is therefore going to be 54.6, take away 48.8, and it gives us 5.8 centimeters. So that's roughly 2 lots of the wavelength if we know that it's about that. But we're not going to get the second maximum. There at the top here is where it's going to be the second order, as it were. This is going to be the first order. So we'll see a point there. We'll see a point on the other side as well. And so we will see 3 bright peaks. We won't see this one here. So I guess we could say, yes, 3 orders of maxima visible on screen. Not an easy question though. So yeah, just be careful if you see a question regarding interference and it's to do with sound, then you might just have to use bog standard trig because the distances are not going to be right. You're not going to have a screen distance that's way, way bigger than the slit separation. 3.1, we have this optical fibre and we have a ray going in here. And this is angle A. Okay, so we have the refractive indexes or indices of both of these. The core has an N of 1.47 and the cladding has a refractive index of 1.41. Okay, what are we being asked? Calculate the speed of light in the optical fibre. Well, we know that refractive index is, well, it tells you how much slower something goes or how much slower light goes in a material compared to air or vacuum. So that's equal to speed of light normally divided by the speed of light in your medium, and we're always going to end up with a number that's bigger than 1, which makes sense. So therefore, swapping these two round, speed of light in the medium is going to be equal to speed of light in a vacuum divided by the refractive index. Like we said, it just tells you how much slower it goes, so divide that by 1.47. We're going to end up with something at about 2, methinks. I'm just going to go 3 divided by 1.47. That gives us, we can just call that, can we? 2.0 times 10 to the 8 meters per second. Calculate the angle A, avec plaisir. We're told that if the ray goes in at an angle greater than A, then it's going to basically refract into the core. So what we have here is this going in, then it's refracting, and then it's going along the boundary like that. So actually we have here two refraction situations, one going in and then the second at the core cladding boundary. So let's deal with this angle here first. I'm going to call this angle, let's just call it phi. So start off with Snell's law. I always like starting off with Snell's law. N1 sine, well, I'm going to go with phi going in is equal to N2 phi 2, I guess we could say, but we know that's 90 degrees, so sine of 90, that ends up being 1. And so therefore, the sine of phi is equal to, so therefore the sine of this angle phi is equal to N2 over N1, which is equal to 1.41 divided by 1.47. So therefore phi is just going to be the inverse sine of those, and that gives us 70, let's go 73.6 degrees, let's be accurate for the time being. So if that's phi there, then that means that this is phi here too. But that's not the angle that we're concerned about when it comes to this situation. It's this angle here, theta. So we can say that theta is equal to 90 minus 73.6. And so that gives us, what's that, 16.4 degrees. Okay, now we have to use Snell's law again. For real this time, we're going to say N1 sine A is equal to N2 sine 16.4. N1 is just 1 because of course it's just air, and N2 is our core, so it's 1.47. So therefore sine of A, let's write this out again, is equal to 1.47 times the sine of 16.4. Therefore A is going to be the inverse sine of all of that, and it gives us 24.5 degrees. Not an easy question that. Lots of people, when they did this, did not realize that it was two refraction questions in one. Very mean of AQA. They should have split it up into two different questions. That's not 3 marks. That's something like 4 or 5 marks there, if you ask me, but whatever. 3.3, now we have it bending. Ray goes in. We're being asked to draw what happens to the ray within the optical fiber. Well, of course, if it's bending, then the normal at the core cladding boundary is going to be turned like that. And so that means that this angle here, called that phi, didn't we? So we can say core cladding angle of incidence is decreased, therefore some light refracts out. TIR does not occur, only partial reflection. 4.1, we have this crazy setup. We have the astronaut there. We have the pole, and the center is about there, and they have a big ball on the other side, and that's A there. Okay, so we're being asked, as the spacecraft rotates, a force that imitates the effect of gravity acts on the astronaut. Explain why. Not an easy question. Lots of people got confused with this one when they did it with me. But basically, we know that in order for A to go around in a circle, this part of it must be being pulled, as it were. There must be a force pulling the box towards the center. So we can say that centripetal force on A toward O, therefore also on astronaut as he or she is in contact with it. 4.2, show that R is given by that. Okay, so we have here our A, and this is L. So of course we're going to be equating forces, aren't we? So what we can say is that the force due to A is equal to the force due to B. This is similar to your binary star systems, isn't it? There is nothing at O pulling A or B. No. The whole point is that the movement of B is producing the centripetal force on A, and A is producing the centripetal force for B. They are spinning or trying to spin around each other. And so ultimately what they end up doing is spinning around the common point O. Lots of people thought that, oh, you know, it's going to be double that because the force is pulling in both directions. No, forces don't work like that. So therefore we can say that, what do we say? Now we could go with MA, that is V squared over r. That would be r8. However, if we do that, we're going to end up with different speeds in there. So that doesn't really help us because A and B are going to have different speeds. So if I call that RB, that is, if I just put that there. So we can't do that. What is common between these two? Well, because they're spinning around each other or trying to, like we said, they are going to have a common angular speed. So we can say omega squared r is equal to mb omega squared r for b. The omegas cancel because they are going to be spinning around at the same period, so therefore the same angular speed, angular frequency. We don't have RB, we have instead L minus RA, so therefore we can see, just rearranging this. Oh, actually not quite. We need to get common things, don't we? We need to get all the RAs on the same side. So let's move over all the M's onto the same side, and then let's put RA over the other side as well. So therefore we can say that MA over MB, just factorising this, is going to be equal to L over RA minus RA over RA, which is just a 1. So therefore ratio of the masses plus 1 is equal to L over RA. So therefore I can say that that is MA plus MB all over MB. I've just basically done the opposite to what I did with the RAs just now. I've just added on MB over MB, that's it. So that's equal to L over RA. Therefore, swapping everything around, we end up with RA is equal to MB times L over the sum of the masses. But again, not a super easy question. Not lots of people got that one right. It's not. This paper, do you know what? I actually like this paper. It's almost a very good paper. They're good questions, some good physics and good maths going on, but they're just making it a little bit trickier, but still pretty good. I like it. It's better than the AS papers, I'll tell you that. Flip me. AS papers for this year were terrible. In this spacecraft, the mass of A is less than the mass of B. Deduce whether the center of mass of A or B rotates with a greater linear speed. Well, like we said, they have the same angular speed, and we know as V is equal to omega r, we saw that R for A is equal to MBL over MA plus MB. Therefore, we can say as MB increases, RA increases. Therefore, as V is proportional to R, VA is going to be greater than VB. A couple of ways you can answer that one, but I've used the equation from above, which is always a good tactic. 4.4, we have a stress strain graph. So we have the masses, and we have G being 3.7 meters per second squared. And of course, this is our acceleration, isn't it? So let's replace that with that if we're talking about centripetal forces and stuff. And maybe it's worth reminding ourselves that A is equal to V squared over R as well, or indeed omega squared R. Okay, what are we being asked then? Suggest a suitable diameter for the rod, 5 marks. Oh my days. Okay, so we know that the force, let's say on A, is going to be equal to, like we said, 3.7, we already have the acceleration, right? Force is equal to MA. And so that's our one, let's go for A, so we're talking about a mass of A, so that's 1.32 times 10 to the 6 times 3.7. Now, a lot of people got confused with this. They added up the masses of both thingies, but like we said earlier, one mass is producing the force for the other mass. So actually, if you think about it in terms of this, if we pretend that B didn't exist and O was a fixed point, would the force or would the stress or whatever on the rod be any less? No, it wouldn't. It would be exactly the same. And so that's where a lot of people went wrong with this question. And yeah, it is confusing, don't get me wrong. So that gives us 4.88 times 10 to the 6 newtons. Okay, so we have this graph here and it's going up like this, and then it's going into the plastic region there. We don't want to get really close to that plastic region. We don't want it to deform plastically. So long as you're somewhere between these 2 points, you should be fine. I'm going to pick a nice number. I don't know, let's pick something like, and that's the thing about this graph. Usually we read the stress and the strain off these graphs, don't we? We find out the Young modulus, but this question has nothing to do with Young modulus. We're just being shown this graph to allow us to choose an appropriate stress. So I'm going to say, I don't know, let's go for 0.2 gigapascals. Doesn't matter which stress you go for, like I said, so long as it's in the middle somewhere. Obviously you don't want to be too small because, well, obviously your rod's going to be massive if you do that then, isn't it? So we're going to go with stress being 0.2 gigapascals. Of course, stress is force divided by area, and 0.2 gigapascals, giga is times 10 to the 9. So therefore we're going to say that that's 2 times 10 to the 8 pascals. Whoops, missed an 8 there. Okay, so therefore, swapping these two round, area is equal to force divided by stress, and so that is our 4.88 times 10 to the 6 newtons divided by 2 times 10 to the 8 newtons per meter squared, or pascals, and that gives us an area of 0.024 meters squared. We're not being asked for an area though, we're being asked for a diameter. We know that area is equal to pi d squared over 4 for diameter. Therefore, diameter is going to be equal to the square root of 4 lots of the area divided by pi. 4 times 0.024 divided by pi, all square rooted, and that gives me an answer at least of 0.175 meters. Mark scheme says anything greater than 0.144 meters and you'll get the mark. Not an easy question. Lots of red herrings there. Question 5. We have this rugby ball being kicked over the crossbar. Show the minimum speed of the ball in flight is about 15 meters per second. So what have they got to do it this way around? Whatever. So it's going over like that. There's the posts. And the point is that we're being told that the speed there is 20 meters per second and we have the angle of 40 degrees. So we're being asked for the minimum speed. Of course, the minimum speed is going to be when it's at the top and it's going horizontally. So min speed at apex has no vertical velocity or vertical component of velocity. Therefore, it's equal to horizontal component, and that's going to be equal to our 20 meters per second times, well, we're turning through the angle to get to here, and so therefore we're going to be multiplying by cos 40. If you don't know where I'm getting that from, then have a look at my easy vectors trig video. And we end up with 15.3 meters per second. 5.2, we're just being asked to prove that this equation is the case. We have t squared and t, so therefore it looks like it's going to be s equals ut plus half at squared, doesn't it? Or in other words, half at squared plus ut minus s is equal to 0. We have our s already, that's 3 meters. What is our acceleration? Well, that's 9.8, isn't it? And so that's then t squared. However, if I'm saying that s is positive going up, that means that down is going to be negative, so therefore our acceleration must be minus 9.8 t squared. So then plus ut, we know we just must have t. What is u initially? That has to be vertical, of course. Well, we've had 20 cos 40 for horizontal, so it's going to be 20 sine 40 for vertical. Looking a little bit messy here, so let's try and tidy this up. Half times 9.8, that's minus, well, okay, 9.81, whatever. So we're going to end up like they have, minus 4.19 t squared plus, what is 20 sine 40 equal to? Sure enough, 12.9. T minus 3 is equal to 0. All they've done, they've just changed around the pluses and the minuses, so we can say therefore that is also true. So there are two solutions, like we said, 4.91 t squared minus 12.9 t. So we're told that there are two solutions to this. Of course there are, because we have t squared in there, don't we? So this is one of the very, very few times where we're going to have to use the quadratic formula. So in our case, that's going to be equal to plus 12.9 plus or minus square root of, well, minus 12.9 squared, so that's just 12.9 squared. Take away 4 lots of 4.91 times 3, all divided by, well, 9.81, isn't it? Because we're just going back to 2 lots of A. So let's just do this one step at a time. This ends up being 10.4, okay, divided by 9.81. So that gives me, if I add it on, that gives me 2.4 seconds. Let's call that 2.38 seconds. Let's go to 3 sig figs, or 0.26 seconds. Okay, so what have we found? Of course, we found the time taken to reach an S of 3 meters. And of course it does that twice, doesn't it? Because it's going up and coming back down, and it's going over the goalpost there. So therefore, T is equal to the longer time to reach goalposts. T equals 0.26 seconds is time taken to reach height of 3 meters on way up. 5.4, another attempt is made. The kick is made from a horizontal distance of 38 meters from the post. Deduce whether the ball can pass over the crossbar. So we're going up and over. There's the goalpost, and then there's 38 meters. So basically, let's use our time from earlier, so 2.38 seconds. We have our velocity, our horizontal velocity, u horizontal. We're going to say that that was, what was that, 20 cos 40. So what was that, 15.3 was it? So then we have a time, we have a speed, we have a distance as well. So there's different ways you can do this. You can either prove that time is not enough, or it is, etc., etc. So there's like 3 different ways you can do this. Let's go with the distance, shall we? Yeah, let's do that. So speed equals distance over time, therefore distance equals speed times time, which is equal to 15.3 times 2.38 seconds. And that gives us a horizontal distance of 36 meters. So therefore, what have you just found out? It's going to reach that point there at 36 meters. So therefore, we can say will be below 3 meters at a distance of 38 meters, therefore not possible. Like I said, you could also compare the times instead, or you could compare the speed needed compared to the speed that we have. 5.5, we have these 2 graphs, speed versus time, or vertical velocity versus time. We have here without air resistance, and then with air resistance. Okay, so 5 marks, so loads of stuff we can write here. It's just a bit weird, isn't it? So let's say that without air resistance, constant gradient, therefore constant acceleration toward ground. With air resistance, initial acceleration, or deceleration in this case, isn't it? Because it's going up, but the air resistance is slowing it down. Faster is greater, but decreases with decreasing speed. We know that the area under both graphs are equal. We can say the area under 0 equals area above 0 for both graphs, as distance travelled upward equals distance travelled downward. We could say that without air resistance, ball stays in motion for longer, therefore will travel further horizontally. There we go. Lots of things there. Weird question. Don't like that question. Question 6, we have a legit log graph. A lot of confusion with these. So it looks like this. It goes down like this. Now, let's just be careful here. We know it finishes at 10 to the 3, but that is 1 times 10 to the 3. And that's where a lot of people went wrong when they did this question with me. And you know what? I got to admit that it is a little bit confusing to begin with. We have 10 to the 6 here, but again, that's 1 times 10 to the 6. And so where it crosses the y-axis up there, that's the next line up. That's going to be 2 times 10 to the 6, and then it goes 3, 4, 5, 6, 7, 8, 9, then 10, or 1 times 10 to the 7. Okay, so let's have a look at the question then. We have a 5 volt power supply, we have a 10 kilo ohm resistor there, LDR, voltmeter there, voltmeter there. Okay, light beam illuminates the LDR. When the light beam is broken, the LDR, blah, 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 blah. Of course, the alarm does sound fine. So when there is light, we're told that the lux is 4.0 lux. When there's no light, it's 1 lux. Those are the thresholds anyway. Okay, so for 6.1, we're just being asked what is the current when we have no light. Okay, so we're just going from our 1 lux, so that's 1 times 10 to the 0. So we're going up all the way here. And well, there's 10 to the 5, or 1 times 10 to the 5, then 2, then 3. So this is 3 times 10 to the 5. So this, when we have no light, is 3 times 10 to the 5 ohms. Okay, so we have 3 times 10 to the 5 ohms. Up here we have, well, 1 times 10 to the 4. So tell you what, should we just call this 300 kilo ohms? This is 10 kilo ohms. We're looking for the current flowing through the system. So therefore, as per usual, comes down to V equals IR. Current is equal to V over R. So that's going to be our 5 divided by, well, 300 kilo ohms plus 10 kilo ohms. So it's just going to be 5 divided by 310 kilo ohms, or 3.1 times 10 to the 5. And sure enough, that gives us 1.6 times 10 to the minus 5 amps, or in other words, 16 times 10 to the 6, or 16 microamps. Okay, what next? Let's just rub that out. 6.2, the alarm sounds when the PD changes by more than 25% of the power supply EMF. Okay, discuss whether the circuit is suitable. Support your answer with a conclusion. Right, okay, so 25% of 5 volts is just a quarter, so 1.25 volts. So that's our target, or what we're trying to compare to. So, okay, what do we say this was? When there's no light, let's write this out again. We have 3 times 10 to the 5 ohms. So therefore, V across the LDR when there's no light is going to be equal to, well, we know that ratio of voltages is equal to ratio of resistances for a potential divider setup. So popping this over the other side. So this is going to be 300,000. So let's just say 300. So 300 divided by, well, added up, that was 310, wasn't it? Times by 5. And we end up with 4.8. Let's get 4.84 volts. Okay, so we got the voltage when there's no light, but what about when there is light? Well, 4 lux, we have to go from here up to here. What does that end up being? Gosh, I don't know. Let's go from 4. It looks like it's bang on between 9 times 10 to the 4 and then 10 to the 5. So I'm going to say resistance of the LDR is 9.5 times 10 to the 4 ohms. Mark scheme says anything from 9.2 to 10 times 10 to the 4. So there we go. So therefore, doing the same thing again, we're going to say that the voltage across the LDR is equal to resistance of the LDR. So I'm just going to say 95 divided by then them added up. So 95 plus that 10 on top, of course, and then times that by 5. So that's just 5 times 95 divided by 105. And we end up with 4.52 volts. Difference in voltage is 4.84, take away 4.52, and that only gives us a change in voltage of 0.32 volts, which is much less than our 25% of 1.25 volts needed. So no, it does not work. Not an easy question, that one, at all. It's a good question though, I like it, but really quite tricky. Again, classic AQA, they expect you to go from A to E all in one go, as opposed to breaking it down into smaller questions, which I wish they really would do, because doing that would still test you guys' physics knowledge. It's just a little bit mean when they do it in this way. All right, multiple choice, I love it. Question 7. What's approximately equal to 3 kilowatt hours? Well, all we have to do is take our 3000 watts, times that by 3600 seconds. Well, that's basically 3 times 10 to the 3 times 3.6 times 10 to the 3. So we should end up with about 10 times 10 to the 6 or 1 times 10 to the 7. So the answer is going to be D. Don't even need to calculate for that one because it's just an estimation. Which is the shortest distance? Oh man, 10 to the minus 19 gigameters, but a giga is 10 to the 9, so therefore this ends up being 10 to the minus 10. Okay, so that's A. What about B? 10 to the minus 14 kilometers. Kilometer, of course, is 10 to the 3. So this ends up being 10 to the minus 11 meters. So it's not going to be A. C, we have 10 to the minus 4 micrometers. Micro is 10 to the minus 6. So this ends up being 10 to the minus 10. So B is still shorter. Then D is 10 to the 7 femtometers. I don't think this is going to be shorter. Femto is 10 to the minus 15. So yeah, this just ends up being 10 to the minus 8. So the answer is going to be B. 9. Which row is the particle matched to the only other fundamental force it experiences? So A, we have a muon. It is EM and it is weak. Yeah, so that's right? Yeah. Ding, ding, ding. Let's have a look at the antiproton. Pi 0 can't experience the EM force, and then D, neutrinos, no, they can't experience the strong force, can they? 10, proton number is 92, and it decays to radon 88. So what can we do to get from radon to that? Okay, so we don't care about the mass number, of course. So let's go down an alpha to get it down to 90. We can do another alpha to get it down to 88. Of course, that's not one of the options, is it? So we're going to have to go down another alpha and then go up with beta. So let's do beta minus. That brings us up to 87. And then another beta minus, that brings us back up to 88. So we should have alpha, 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 beta minus, and the only one that has that is A. So that's our answer. 11, we have a Feynman diagram. We have, oh boy, so we have this going in here. Blah, blah, blah. We have a beta plus being made, and then we have whatever being made there. Right, so if it's beta plus being made, then we know that it's going to be the opposite of beta minus, and so beta minus is a neutron turning into a proton and an electron, isn't it? And beta minus particle, that is. So therefore beta plus is a proton turning into a neutron and a positron. So therefore it looks like it's going to be a proton going on here, neutron coming out, and then we have obviously an electron neutrino, because it's an anti-electron neutrino for beta minus, isn't it? But we're being asked in terms of quarks. It's the POOD and the NUD. So all that's happening is an up quark is being turned into a down quark. So it's going to be A again. Quark combination, strange anti-up. Well, I can say, oh, that's going to be a K minus. What's true for the particle? It has a barrier number of 1. No, because it has to have a barrier number of 0, because it ain't no baryon. B, it has a charge of minus 1.6 times 10 to the, yeah, that's right, because anti-up is minus 2/3, strange is minus 1/3, so altogether minus 1. That is minus 1e, which is 1.6 times 10 to the minus 19. It's not a pion because pions can't have strangeness. It has a strangeness of minus 1/3. No, there's no such thing as a strangeness of 1/3. Strange quarks have a strangeness of 1 minus 1. 13, monochromatic light, photon energy of that, many joules. Incident, the maximum speed is 4.2 times 10 to the 5 meters per second. What's the work function of the metal? Okay, so EK max, that is equal to HF, which is the energy of our photons. So I'm just going to say that, take away the work function. So therefore, the work function is equal to the photon energy, take away the kinetic energy. And we know that's true, don't we? Because, well, it's the sort of energy tax that's needed before an electron is emitted. So we have here 4.1 times 10 to the minus 19, but then we need to take away the kinetic energy, and so therefore we're going to have to say this equals half times mass, 9.1 times 10 to the minus 31 for an electron, times the speed squared, which is 4.2 times 10 to the 5 squared, and we end up with just 2 sig figs, 3.3 times 10 to the minus 19. So the answer is gonna be B. 14, what's true about mercury vapor in a fluorescent tube? A, it absorbs photons of UV light. No, that's what the coating does. B, it absorbs photons of visible light. Well, no, because, well, that doesn't happen anyway, does it? You know, that's the opposite. C, it emits photons of visible light. No, that's what the fluorescent coating does. D, it emits photons of UV following ionization or excitation. Yes, that is correct. 15, we have 3 energy levels. So we have n equals 0, n equals 1, n equals 2. You might call them n1, n2, n3, whatever. Okay, so we have different frequencies. What's the difference in energy between the ground state and energy level 1? Okay, point is that we have 3 different photons that can be emitted, don't we? This one here, and then these 2. If we're looking for N1 to the ground state, we're looking for this one here. So this is going to be the energy in the middle. So what frequency is that going to relate to? Well, we have 3 frequencies, with the smallest one being the times 10 to the 14. Right. Okay, so the middle one is going to be 2.46 times 10 to the 15. That nearly caught me out. I thought they were all 15. So therefore, we know that E is equal to HF. So that is 6.63 if we're looking for the energy, times 10 to the minus 34 times 2.46 times 10 to the 15. Looking at my answers there, they're all different. They're all the same power, same order of magnitude. So I think I can just do 6.63 times by 2.46, and that gives me 1.6 something. And so I can see that C is the only possible answer there. 16, which one gives a particle with a greater kinetic energy and the particle with the longer de Broglie wavelength? Right, okay, so kinetic energy is equal to half mv squared, and de Broglie wavelength is equal to h over mv. Yeah, they're traveling the same speed, right, okay. So E is proportional to m, and lambda is inversely proportional to m. Right. So therefore, if it's heavier, which a mu1 is, then the mu1 is going to have the greater kinetic energy, and then if it's lighter, it's going to have the greater wavelength, and so that's going to be the electron. So the answer is B. 17, we have displacement distance and displacement time graphs for a wave. What's correct for the wave? A, the amplitude is 3 meters. No, the amplitude is 1.5 meters, so it's not that. B, the wavelength is 6 meters. No, the time period is 6 seconds. That's where they're trying to catch you out. C, the speed is 8.3 meters per second. Oh, gosh, fine. So V is equal to F lambda. So there's going to be, well, we've got time period, so we can just say, fine, lambda over the time period, so 1 over time period times the wavelength. So there's going to be 0.5 meters divided by 6. That's the time period. And so, no, it's not going to be that, is it? That's going to be 0.083 meters per second. So that ain't right. And then probably going to be D, but let's check the frequency. Well, we know that's equal to 1 divided by time period. So it's 1 divided by 6. And yeah, that's going to give us 0.17 hertz. So that's our answer. 18, we have P, Q, and R. It is a stationary wave, right? So we know that points on a stationary wave can only either be in phase completely or completely out of phase. It doesn't matter where they are on the loop, it just matters what side of equilibrium they are. So let's have a look. A, P is in antiphase with R. That's true. P has the same amplitude as Q. Yeah, that's true. That's going to be our answer. Yay! So yeah, P and Q are going to be in phase, out of the same amplitude. R is out of phase with P and Q, and it has a different amplitude from both of them as well. 19, diffraction grating. Okay, so we know that we're going to be writing down n lambda equals d sine theta. So we're told the second order maximum occurs at the same angle for the third order maximum. Right, okay, so this is proportionality. So d is staying the same and theta is staying the same. So therefore we can say that n1 lambda 1 is equal to n2 lambda 2 because they are inversely proportional to each other. So let's just replace, so we can say that this is the second order times 650. We don't need to change into meters because this, of course, is just proportionality, equals 3 times lambda 2. I'm just going to call that lambda. So therefore, that's going to be our answer. So the answer is 433 nanometers. So the answer is C. 20. Oh, the diagram is drawn to scale. What is the magnitude of resultant? Well, fine. All we have to do is move one of these. Let's move that one there, top and tail it. That's our resultant. All you have to do is say that, well, this smaller vector is 5 newtons. I don't know what it's going to be the size on your paper when you print it out. Whatever, you just have to say, well, if it's 5 centimeters, then that means that it's 1 centimeter per newton. Measure this resultant force, and in my case, I'm going to say that it ends up being 9.6 centimeters, so therefore that ends up being 9.6 newtons. We have now this plank. Oh yeah, this one's complicated, isn't it? That's 0.2 meters. That's 1.8 meters between. And then we have 1.4 meters. The man weighs 800 newtons, and this is what confused me about the question the first time I did it. It's a little bit confusing, the diagram is. So the plank weighs 1,200 newtons, so it's going to be right from the middle. What is the horizontal distance between P and the center of mass of the man? Yeah, see, that's so, the way they word it, basically, how far is the guy going to be away from P? That's so stupid. It's because the guy standing there, it's not there. There's our pivot. The dude's going to be here instead when it starts to tip. And he weighs 800 newtons. Okay, so this is just moments. So we can say that this distance here, if that's 2 meters, and it's 3.4 altogether, then that means that it's 1.7 between. Ugh, so much effort. So that's 2, so that's going to be 0.3 meters. Fine. So therefore we can say that 1,200 times 0.3 is equal to 800 times this distance here. So therefore the distance ends up being 1,200 times 0.3 divided by 800. Of course we can cancel some zeros. So this ends up being 0.45 meters. That's our distance there. So we just add on then our 1.8 meters and we end up with 2.25 meters. So our answer is B. It's a lot of work for a 1 marker. Blummin' heck. 22. Where's the center of mass? Of course, the center of mass needs to be going through where the bob is, or the line of action and all that jazz, in order to not be doing that. Lots of people, but this point here is the center of mass. Can't be true because that's ignoring all of this mass up here. Center of mass has to be in the empty space. So our answer is C. Coin going off the top of a desk, which shows the acceleration and momentum. Well, of course, acceleration has to be straight downwards. So therefore it can't be A, it can't be B. Momentum has to be in line with the velocity at that point. So it has to be tangential to the motion. So therefore it's going to be F. So our answer is C. 24. Formula 1 car uses up its fuel, causing its lap time to decrease. Why? Oh gosh, okay. The acceleration of the car increases? Yeah, that has to be true, because if F is equal to ma, force is going to stay the same, but if mass goes down, the acceleration must go up. So that has to be our answer. Let's just check the other ones. B, drag force decreases. No, because surface area isn't changing. And actually it's going to be getting faster, so the drag force is going to increase actually, but whatever. C, the maximum speed of the car increases. No, that's not going to be true, because when we reach terminal speed, air resistance isn't going to change really. Tires become worn, reducing the friction. No, we want friction on the road, don't we? 25, we have a force time graph, so naturally we are going to find the area underneath. And so we're going to say this area is about half times 0.6 kilonewtons, so 0.6 times 10 to the 3, times that by the time. So, because there's 2 triangles, isn't it? I can do that. So 16 times 10 to the minus 3, they cancel, pounds of 10, so therefore it's just going to be 0.3 times 16. So that gives us what, 4.8 Newton seconds worth of momentum. We've been asked for the kinetic energy. We could, you know, find out what the equation is, but let's just find out what the speed is, shall we? So we can say that momentum is equal to mv, so therefore speed is equal to momentum over mass. That's going to be 4.8 divided by, well, it needs to be in kilograms, so divided by 0.046. It's going to give us something like 100, isn't it? Which makes sort of sense for kind of speed that we would get for a golf ball. And so therefore EK is equal to half mv squared, so it's equal to half times 0.046 times 104 squared, but it's just an estimation, so we don't care too much, and we end up with about 250 joules. So our answer is C. 26. Two wires have the same extension, so extension is staying the same for the same load, so force is staying the same as well. We're changing the diameter and density. Oh, density and the Young modulus E. Oh, great. Okay, but its diameter is 2d. Okay, so Young modulus we know is equal to FL over A delta L. Now, here's the problem, is that we're not given length, we're given density, aren't we? So we need to replace length with something to do with density. Density is equal to mass divided by volume. We're told that mass is the same. Right, okay. So we can say that density is proportional to 1 over volume. Volume is proportional to, well, it's proportional to length and area. So 1 over length times area. So therefore, we can say that swapping length and density, we can say that length is proportional to 1 over density times area. This is not an easy question, this one. So we can then pop that in. Well, let's just go down here. We know that if F and delta L are staying the same, that means that Young modulus is proportional to L over A. Oh, we've already done it. Right, okay. So they have the same length. We're already told that. Oh, gosh, what am I doing? Right. Okay, so that just means that, yeah, cool. Density is proportional to 1 over A. Therefore, density has to be then proportional to 1 over diameter squared. So if the diameter is double for Y, then that means this goes up by times 4, which means the density goes down by a factor of 4. So therefore, the density has to be down by 4. So it can't be A and it can't be B. Right, so we dealt with the density. Now let's deal with the Young modulus. So we know the length is the same, fine. So it's proportional to 1 over area. So like we saw, oh, that's easy. Sorry, what am I playing at? Confused myself because of the whole area thing. So therefore the Young modulus is going to be going down by a factor of 4 as well. So therefore the answer has to be C. Still not a super easy question though. That's 2 questions in one. It's not very nice. 27, we have this circuit here, 4.2 volts. Okay, very neat drawing. Well done, me. What are the readings on the voltmeter when the switch is open and when the switch is closed on? So, voltmeter. Are we assuming that the voltmeter has infinite resistance? I guess so. Oh, right. Okay. Technically, oh, this is not a nice question. Technically, that voltmeter is then going to be recording the terminal PD. So it would be like if the voltmeter was plugged straight into the terminals of the battery. So it should be measuring the EMF. So it should be 4.2 volts when the switch is open. When it's closed, on the other hand, well, we have 4.2 being split between 10 ohms and, well, this is just going to be 20 ohms, isn't it? So it should be split 2 to 1. So that should be, well, it's 4.2, nice numbers, isn't it? It's 1.4 volts and 2.8 volts. So therefore V should be reading 1.4 volts when it's closed. So the answer is D, but I will forgive you for thinking that the answer was C. Okay, so we have here internal resistances, and we have the load resistance of 2.4 ohms. What is the current in the resistor? So basically the total current. So if we're looking for the total current, let's just write down Ohm's law. V tote equals I tote times R tote. And we're looking for this. So therefore I is going to be V over R, but the total voltage, total resistance. So total voltage is going to be just that 1.5 volts. They're in parallel. Divide that by, well, we have 1.6 to 1.6, that's 0.8 ohms because they're in parallel. And then we just need to add that on to the 2.4. So basically 1.5 divided by 3.2. And we should find that the answer is 0.47 amps. So the answer is B. It all comes back to V equals IR. 29, we have power supply, blah, 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 blah. Let's draw this out real quick. What's the reading on a voltmeter? Oh, okay, right. So we're told that the wires are the same length. The wire diameter 2D, right. We know that resistance is equal to rho L over A. They're the same length, right? Yeah, same length. So therefore, resistance is proportional to 1 over A. So similar to our Young modulus question just now, resistance is proportional to 1 over D squared. So therefore, if this is double, then the whole thing is times by 4. So resistance goes down by a factor of 4. Therefore, we know that Y is going to have a quarter of the resistance of X. So we can say, let's say 4 ohms and 1 ohms, doesn't matter, it's just the ratio. So therefore, 30 is going to be split 4 to 1. So it's going to be into 6s. So it's going to be 24 volts and 6 volts. So the answer should be D. 30, classic question, pendulum and mass spring system, blah, 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 blah. What's going to happen to the pendulum and the mass spring system? Well, the mass spring system is not going to do anything because there's no G in our equation for our spring system, no G, so therefore T is going to stay the same. For our pendulum, on the other hand, 2 pi root L over G, so therefore we can say that T is proportional to 1 over root G. So therefore, if this goes to a fourth, that means that this goes to a half, so that means that T doubles, which makes sense. If it's on the moon, it should take longer to swing, so it should be 2T, so it looks like our answer is going to be B. Finally, 31, particle is oscillating, blah, blah. What's the maximum kinetic energy of the particle? Kinetic energy, well, we know that EK is equal to half mv squared. V max in this case, if we're looking for the maximum, and we know that V max is equal to 2 pi FA. We're being given it in terms of time period though, so we're going to replace F with 1 over T. Let's pop this in here. So therefore, EK is equal to half m times 2 squared is 4 pi squared a squared over T squared, and a half and 4, that just ends up being 2, so it should be 2m pi squared a squared over T squared, and so our answer looks like it's gonna be D. If you found this helpful, please leave a like. Like I said, consider clicking the super thanks button, really helps me out a lot, especially with these past paper videos. If you need any extra help, join the Discord, link in description, lots of helpful people there. And if you click on the card, it'll take you to the playlist with all of the past papers in. Good luck with your studies. I'll see you next time. Bye for now.